The first pre-dawn chill of a late autumn morning in Toulouse always carried a particular quality, a crispness that seemed to sharpen the senses. It was 4:17 a.m. on October 26, 2023, and the vast, silent hangars of Airbus stretched like sleeping leviathans under the distant glow of city lights. Inside one such cavern, a single figure, Dr. Anya Sharma, head of advanced propulsion systems at Airbus, stood before the skeletal frame of what was, for now, simply designated the ZROE demonstrator. Her breath plumed faintly in the cool air, a transient cloud against the permanent gleam of polished steel and intricate wiring. This was not the sleek, finished article of future flight, but rather a raw, exposed anatomy, a complex tapestry of fuel cells, cryogenic tanks, and high-voltage conduits, all painstakingly arranged around what would eventually be a modified A380 airframe. The silence was profound, broken only by the occasional hum of distant machinery and the almost imperceptible whir of cooling fans within the demonstrator itself. It was a silence pregnant with expectation, a tangible manifestation of the global aviation industry's pivot. Dr. Sharma ran a gloved hand along a section of the hydrogen fuel cell stack, its surface cool and smooth. This moment, solitary and deeply technical, represented more than just an engineering milestone. It was a cultural inflection point. For decades, the roar of jet engines had been synonymous with progress, with the boundless reach of human ambition. Now, the aspiration was for silence, or at least a whisper. The narrative, once dominated by speed and capacity, was recalibrating towards an urgent, existential quest for sustainability. The ZROE project, as detailed in numerous industry briefings and academic papers, 10-11, is a testament to this shift, aiming to achieve net zero emissions by 2050. The challenge, as Dr. Sharma knew intimately, lay not just in the audacious engineering of hydrogen combustion or fuel cell integration, but in the wholesale reimagining of an entire global infrastructure, from airport charging points to regulatory frameworks. 6. The promise of a more electrical aircraft, EMIA 3, was no longer a distant theoretical concept but a tangible, if still nascent, reality unfolding in the precise geometries of this very hangar. The smell of ozone and freshly machined metal hung faintly in the air, a scent of the future. The current landscape of the aviation world of flight is defined by a paradox, a relentless pursuit of revolutionary technological advancement juxtaposed against the enduring inertia of established players and regulatory bodies. The dominant narrative is undeniably green, driven by an existential imperative to decarbonize. This push is most visibly spearheaded by a diverse array of innovators, from legacy aerospace giants to nimble startups, all vying for leadership in the next generation of propulsion and operational paradigms. In the realm of electric flight, the conversation spans the entire spectrum, from urban air mobility, UAM, to regional and even nascent long-haul concepts. Companies like Archer Aviation and Joby Aviation are at the forefront of the UAM revolution, with both having achieved significant milestones toward certification and commercial operation of their electric vertical takeoff and landing (eVTOL) aircraft. Archer, for instance, in partnership with United Airlines, aims to launch commercial service by 2025, demonstrating a clear path to market entry. Joby, similarly, has secured substantial investment and regulatory progress, underscoring the serious capital and human talent being poured into this sector. However, the true game changers for broader aviation remain the development of larger electric aircraft. Companies like Aviation, with its Alice aircraft, are pushing the boundaries for regional electric travel, while the more electrical aircraft, EMIA concept, as outlined in Source 3, signifies a systemic re-engineering across diverse aircraft types, reflecting a fundamental shift in power and control systems towards integrated electrical solutions. Airbus, a titan in the traditional aerospace sector, is also heavily invested in electric and hybrid electric research, recognizing the need to adapt its vast product portfolio for a sustainable future. Their eFan-X demonstrator, though now concluded, provided invaluable data on hybrid electric propulsion, influencing subsequent research and development programs. Hydrogen, too, is emerging as a formidable contender in the decarbonization race. Airbus is arguably leading the charge among major manufacturers with its ZEROe concept aircraft, publicly committing to bringing a hydrogen-powered commercial aircraft to market by 2035. This audacious goal has galvanized the industry, prompting significant investment in research and development not only for the aircraft themselves, 10, but also for the critical infrastructure required for hydrogen production, storage, and distribution at airports, 11, 12. Rolls-Royce, a key engine manufacturer, is actively developing hydrogen combustion technologies, collaborating with partners to conduct ground testing of hydrogen-fueled engines. Universal Hydrogen, a startup, is taking a different approach, focusing on modular hydrogen capsule technology designed to retrofit existing turboprop and regional jet aircraft, aiming for a quicker path to market by leveraging existing airframes. The leadership in this space is not singular, but rather a complex ecosystem of aircraft manufacturers, engine makers, energy companies, and innovative startups, all driven by the dual pressures of environmental mandates and the immense commercial opportunity of defining the next era of flight. The sheer scale of investment and the ambitious timelines underscore the industry's conviction that these sustainable pathways are not just aspirational, but an inevitable reality. The contemporary aviation world of flight is not merely defined by its ambitious green horizons and digitized operations, but by the meticulous, often unseen, craftsmanship that underpins every technological leap. This is a realm where the abstract promise of sustainable flight solidifies into tangible materials, precise engineering, and rigorous processes. Consider the electric aircraft, a cornerstone of the decarbonization agenda. Its very existence hinges on breakthroughs in battery technology, which, as Source 7 notes, are evolving rapidly. This evolution is a testament to the highly specialized craft of materials science, where chemists and engineers work at a molecular level to enhance energy density, reduce weight, and improve thermal management in lithium-ion or solid-state cells. Companies like CATL or Panasonic are not just producing batteries. They are crafting the fundamental energy storage units that dictate an aircraft's range and payload, often involving proprietary electrode formulations and novel packaging techniques to ensure both performance and safety under extreme aerospace conditions. Beyond energy storage, the craft extends to the very structure of these new aerial vehicles. The more electrical aircraft, MEA concept, detailed in Source 3, demands a profound reevaluation of traditional airframe design. This involves an intricate dance between aerodynamics and electrical integration. Airframers like Airbus and Boeing and newer entrants such as Aviation with its Alice aircraft are pushing the boundaries of composite materials. The handlaying of carbon fiber prepregs, followed by autoclave curing, is a highly skilled process that ensures structural integrity while minimizing weight, a critical factor for electric propulsion systems where every kilogram saved extends flight duration. This isn't merely assembly, it's a bespoke fabrication, often tailored to specific stress points and aerodynamic profiles, requiring highly trained technicians and sophisticated robotic systems to maintain exacting tolerances. The integration of hydrogen propulsion, as discussed in Sources 10 and 13, introduces another layer of sophisticated craftsmanship, particularly concerning fuel storage and distribution. Designing cryogenic tanks capable of holding liquid hydrogen at extremely low temperatures, often below -250 degrees Celsius, demands specialized metallurgical knowledge and advanced welding techniques to prevent leaks and ensure structural resilience against thermal cycling. Companies like Safran, developing hydrogen fuel cell systems, invest heavily in the precise engineering of these components, where even microscopic imperfections can have catastrophic consequences. The craft here is not just about building, but about anticipating failure modes, designing in redundancies, and validating every component through relentless testing cycles that simulate decades of operational stress. This deep dive into technique, materials, and process reveals an industry where the future is being built, quite literally, by hand and by highly specialized machines, one meticulously crafted component at a time. The grand narrative of flight, from its nascent, audacious beginnings to its current sophisticated complexities, is inextricably linked to the vision and relentless ingenuity of specific individuals and the industrial powerhouses they forged. These are the architects of the skies, whose contributions have not merely advanced technology, but have fundamentally reshaped our perception of possibility. Consider the foundational work of the Wright brothers, Orville and Wilbur, whose 1903 Kitty Hawk flight, though primitive by modern standards, was a triumph of applied physics and mechanical engineering, establishing the basic principles of controlled flight. Their iterative design process, culminating in the Wright Flyer, set the precedent for systematic aeronautical development. In the 20th century, figures like Igor Sikorsky, an emigrant from Kiev, Ukraine, revolutionized rotary wing flight. Sikorsky's VS-300, first flown in 1939, marked a pivotal moment in helicopter design, moving beyond the experimental and towards practical utility. His subsequent company, Sikorsky Aircraft, became synonymous with robust, versatile helicopters, from the H-19 Chickasaw to the Black Hawk series, critical for both military and civilian applications. These machines embody a direct lineage from his initial vision. Similarly, the relentless pursuit of speed and efficiency in commercial aviation owes much to figures such as Kelly Johnson, the legendary engineer at Lockheed Skunk Works. Johnson's design philosophy, encapsulated in his 14 rules, led to iconic aircraft like the U-2 spy plane and the State Route 71 Blackbird, pushing the boundaries of aerodynamic performance and materials science. While these were military projects, the methodologies and material advancements often trickled down, influencing subsequent commercial designs. The contemporary landscape of sustainable aviation is similarly being shaped by a new generation of masters and makers. Didier Everard, for instance, formerly of Airbus and now a key figure in the electric aviation startup Vertical Aerospace, exemplifies the transition of expertise from legacy aerospace to disruptive technologies. His experience in developing large commercial aircraft at Airbus is now being applied to the complex certification processes and manufacturing scalability challenges of electric vertical takeoff and landing, EVTOL, aircraft, as highlighted by discussions around certification complexities. Source 2. Companies like Embraer, under leadership that champions innovation, are not merely adapting existing airframes, but are fundamentally rethinking propulsion. Their collaborative projects, such as the Energia family concepts, demonstrate a commitment to hydrogen and hybrid electric solutions, evolving from their existing E-Jet regional aircraft expertise. These endeavors are not just about building new planes. They are about constructing an entirely new infrastructure for flight, demanding a mastery of novel energy systems and complex regulatory navigation. Source 6, Source 7. The houses of Boeing and Airbus, while massive and often slow to pivot, remain crucial. Their ongoing research into hydrogen-powered aircraft, Source 10, and the more electrical aircraft concept, Source 3, showcases their enduring capacity to invest in fundamental shifts, leveraging vast engineering resources to address the global imperative for decarbonization. The contemporary aviation landscape, while undeniably fixated on a future of sustainable flight and digital integration, simultaneously grapples with the profound weight of its own heritage. This dynamic interplay between the revolutionary and the established is not merely an academic exercise, but a lived reality for manufacturers, operators, and regulators alike. Consider the foundational principles of aerodynamics, meticulously refined over a century by pioneers like the Wright brothers, which still underpin the design of every cutting-edge electric vertical takeoff and landing (eVTOL) aircraft. While companies like Joby Aviation and Archer Aviation push the boundaries of urban air mobility with their distributed electric propulsion systems, the fundamental physics of lift, drag, thrust, and weight remain immutable. Their certification processes, though novel in application, are still rooted in the rigorous safety paradigms established for traditional commercial aircraft, a testament to the enduring value of hard-won experience. 2.